Hello, and thank you for viewing this presentation. My name is David Britt, and today we will be going through SNMP concepts and principles. This is the first of what will be a three-part series. We'll break today's presentation into four parts: an introduction, basic concepts, how the various parts of the SNMP environment interact, and then we'll go through some flows illustrating a properly operating environment. This first presentation is an introduction to SNMP, both as a protocol in general as well as how we implement it on the IBM z/OS mainframe. The second presentation will cover configuring the SNMP environment on the z/OS platform, and the third will address troubleshooting and debugging tips and tricks. I don't claim to be a very funny person, but that doesn't mean I don't try. If I fall short, don't hold it against me. Let's get started with some basic SNMP concepts. These will hold true for SNMP whether or not you're on the z/OS platform. SNMP stands for Simple Management Networking Protocol. In the IBM Communications Server IP Configuration Guide, we provide this nice, albeit lengthy, definition. SNMP is a set of protocols that describes management data and the protocols for exchanging that data between heterogeneous systems. The protocols include both the description of the management data, defined in the Management Information Base, or MIB, and the operations for exchanging or changing that information. By implementing common protocols, management data can be exchanged between different platforms with relative ease. While the definition on the previous page is accurate, it's not exactly the most easily digestible description. So let's break it down a little in order to better understand it. SNMP is architected by RFCs and as such is platform independent. In other words, not only can an SNMP environment be set up in many different scenarios and platforms, you can also have individual components of a single SNMP environment running on different platforms. For example, it's not uncommon to see an environment in which the SNMP agent is running on a z/OS mainframe, communicating with an SNMP subagent running on a non-IBM router, and providing data to a PC-based SNMP manager. We will discuss these different elements later in this presentation. Ultimately, however, the purpose of the SNMP agent is to exchange and manage data about a system, piece of hardware, or specific application. Let's take a look at the different components which make up an SNMP environment. There are four types of components. The Management Information Base, which we will refer to as a MIB, is the collection of data which can be managed and exchanged in an SNMP environment. The SNMP agent is a bit like the primary server, although SNMP doesn't exactly conform to the typical client-server relationship. It's also called the SNMP daemon, or on some platforms, OSNMPD or SNMPD. The SNMP subagent is sort of like a secondary server that interfaces with the SNMP agent. Finally, there's the SNMP agent, which is the end user. Let's take a closer look at the MIB. SNMP agents and subagents do not define what information is available in an SNMP environment. Instead, they simply provide the framework by which the data can be accessed. A MIB, however, does nothing but define the data and is designed to be extensible in order to allow future additions, adaptations, and deprecations. There is no single MIB, but rather many MIBs, each specific to a particular type of information. For example, there are several RFC architected MIBs, such as the System, Interface, IB, and TCB bases. Each of these contains data specific to the indicated topic. But not all the MIBs in an SNMP environment are standardized. The extensible nature allows individual products or vendors to create their own MIB in order to manage and exchange non-standard data through SNMP. IBM Communications Server has several of their own, including the 3172 MIB, an IBM-specific TCP/IP MIB, and a Telnet MIB. So that's a conceptual description of the MIB, but it would help if we could take a look at the MIB in a more tangible fashion. MIBs are organized into a tree structure that each branch is a classification of data and each leaf is a specific piece of data. What we see here is the topmost part of the standardized tree. For the communication server, the MIBs we supply fit in this yellow path. It is also important to understand that each of these branches has a number associated with it. These can be strung together in a dotted decimal format in order to create a unique identifier for each path or object. So if you wanted to tell someone how to get to the internet path, instead of saying root, ISO, identified organization, DoD, internet, you could simply say 1.3.6.1. This string of numbers is called the object ID, or OID for short. In fact, what we'll see when we discuss the interactions with the SNMP components is that in order to avoid ambiguity, interaction using only the OIDs occurs, and the textual representation really only exists to help out us humans who don't find numbers alone to be quite descriptive enough. Underneath the Internet branch, there's a myriad of different branches spanning multiple MIBs, products, and protocols. Many of these are defined by RFCs, but many are also vendor-specific, including the IBM Communication Server MIBs. Rather than list all of them here, we provide in the IBM Communication Server IP System Administrator's Commands Manual a list of all the MIBs shipped with the CommServer product, both RFC architected and IBM specific. So we've looked at how the MIBs fit into the tree structure and discussed what branches represent, and now we need to look at what the leaves mean. When we're talking about the thing at the end of a MIB path, we could actually be referring to one of two things: singular objects and table objects. Singular ones are static, their OID never actually changes. Also, there is only one of them for every SNMP environment. A good example of this is the system descriptor, or sysdesker. For any SNMP environment, there will only be one description for that system. For objects like this, the OID always ends with a .0. For example, the path leading up to sysdesker is 1.3.6.1.2.1.1.1, and the sysdesker object itself is the 0. Tables, on the other hand, represent objects which are more dynamic in nature, and the table may expand or contract throughout the life of the SNMP environment. Tables are made up of entries, indices, and instances, all of which affect how the ultimate object is encoded into an OID. An example of this is the IP address table, which represents the current IPv4 addresses active on a system. The IP adder table OID is 1.3.6.1.2.1.4.20, and this is actually just a branch. Off of this branch is a single entry, IP adder entry, which has a value of 1, bringing the whole OID to 1.3.6.1.2.4.20.1. Beneath this entry are 5 indices, 1 through 5, each representing a different attribute with which each instance in this table will have. At this point, none of these paths constitute any actual data. The next step in the path is the actual leaf of the tree, a dynamic instance which is created beneath each index in the table. For example, let's assume that the system in question has 2 IPv4 addresses. In the IP adder table, we would then have 2 instances, or leaves, under each of the table's entries indices. Each instance is incrementally assigned a value, and that value becomes the end of the OID. In this example, you'll see we have a set of indices which end with 1, and these all relate to the first entry. Then we have another set all ending with 2, all of which apply to the second entry. This tends to be a bit difficult to swallow at first, so let's try a different way of explaining it. This is your table, IP adder table. This is your entry, IP adder entry. This is your index, IP add int net mask. And as we have 2 instances, this is instance 1, and this is instance 2. Finally, let's just drive the concept home by looking at it like an actual tree. A quick tip in case it hasn't already sunk in: if you're looking at an object whose OID ends with 0, you know it's a singular object. If it doesn't, then it must be a value in a table. Now that we're experts in the concepts of the MIB, let's take a look at the SNMP agent. As I mentioned previously, the agent tends to have a few other names: OSNMPD, SNMPD, the SNMP daemon, and BERT. Just kidding about the BERT. Again, the SNMP agent would be a sort of a server if the SNMP environment conformed to the typical client-server relationship. It's responsible for managing MIBs specific to the SNMP environment, like the system MIB. It's also responsible for managing the connections with the various subagents active in the environment, fielding and responding to requests from managers, gathering data from subagents when needed to fulfill a manager's query, and generating traps to management stations. We'll talk about more of these a little later. The subagent is neither a client nor a server, but actually sort of an ancillary server that assists the agent. While CommServer ships one and only one agent, there are multiple subagents which are provided with the product. These include the TCP/IP subagent, which provides information related to the TCP/IP stack, the OSI Express Direct subagent, which provides information about the OSI cards, the TN3270 subagent, which provides information about the Telnet application, the OMP route, also called the OSPF subagent, which provides information about the routing daemon, and the SLAP-M2 subagent, which provides information about the policy agent and its associated policies. In addition to this, other subagents are available from IBM, such as WebSphere and NetView subagents, as well as from non-IBM vendors. Subagents have 4 roles within the SNMP environment. They are responsible for connecting into the SNMP agent and then registering the MIBs they support with the agent. Registering the MIBs allows the agent to determine what subagent to poll when a query arrives for data not supported by the agent itself. Subagents are also responsible for managing the data in their MIB. In many cases, this requires that the subagent communicate with a related application to obtain the data it needs to populate its MIB. For example, the TCP/IP subagent uses ioctl calls to query data from the TCP/IP stack and then places that data into the appropriate MIB structures. Finally, subagents may also generate traps to the SNMP agent. Again, we'll talk more about that later. Finally, we have the manager. The manager is the end user of the SNMP environment and as such could be considered a client. The manager generates queries to the SNMP agent for information and listens for any traps the SNMP agent might generate. The manager also presents the results of queries of any received traps in a format usable by the end user, which is typically a system administrator. The presentation might be a graphical, real-time, or even just a formatted report display. Some managers simply echo the data to the user as is. The ComServer product does ship a Unix system services-based command line manager, but is not intended for production usage. Instead, its purpose is primarily to assist in setting up and testing the SNMP environment. Now that we've seen the components, let's talk about how they interact with one another. Managers and the SNMP agent communicate over UDP, by default using port 161. This, of course, can be configured differently for a non-standard setup. Communication between subagents and agents can take place over UDP, TCP, or through an AF Unix socket. Typically, subagents running on the same LPAR as the SNMP agent will use the AF Unix socket, and in fact, all the subagents supplied with the ZOS communication server use this approach. The use of TCP or UDP sockets allow subagents running remotely, such as on a router or in the network, to also connect to the agent. But what exactly are these communications, you ask? Well, the SNMP environment is all about making information available, much like a library. Imagine that you've just walked into a library and have lots of questions. If your questions are of a nature specific to the operation of the library itself, it's likely that the librarian can assist you. For example, what time does the library close? Where is the bathroom? Can you help me with this card catalog? These are all questions that the librarian should be able to answer. But what if your questions aren't related to the library itself, but rather are of an academic nature?
What is the airspeed velocity of an unladen swallow? Huh? I don't know that.
She'll most likely need to consult an expert in that area, who will then provide to her the appropriate information, which then can be passed on to you.
What do you mean? African or European swallow?
Now let's translate this into the SNMP environment. The SNMP manager is really like the library patron. The SNMP agent is like the librarian, and the bird experts are actually subagents, and there's usually multiple of them. Now imagine that an SNMP manager generates a query to the agent, and that the query is for an object in a MIB supported by the agent. The agent simply finds the requested data and sends it back to the manager. What's your system uptime? That many hundredths of seconds. Now imagine the manager sends another query, but this time it's for something that's not in a MIB supported by the agent. Instead, it's for data in the TCP connection table, which is supported by the TCP/IP subagent. The agent, upon receiving the request, recognizes the data as being in a MIB that was registered by the TCP/IP subagent and correctly forwards that request on. The subagent sends back the requested information, and the agent sends that back to the manager. There are many types of requests a manager might initiate to an agent. Basic ones entail a single request for a single piece of data, resulting in a single response with a single value. These include the GET, GETNEXT, and SET requests. The more complex requests entail either a series of multiple requests and responses, like a walk, a single request for multiple values, like a GET bulk, or a series of requests for multiple values, like a bulk walk. The GET request is very straightforward. The manager specifies a specific object, and the agent returns the value of that object. Note that in this interaction, the manager must know the full OID of the object. Thus, the request is typically for a static, singular object. It's possible that the manager might request a dynamic object using a GET, but this would typically only happen if the manager preceded the GET request with other requests that provided information on which instances were currently available within the table in question. The GETNEXT request is similar to the GET in that the manager requests a single object and gets back a single value. The difference, though, is that the SNMP manager does not need to know the full OID of the requested object in order to make the request. Instead, it simply specifies a starting point, and the agent returns the next valid instance following that starting point, not including the starting point. For example, the manager might request 1.3.6.1.2.1.1.9. This is not a valid object, but rather is a table. The agent locates the first non-null instance after the table's OID and returns the value. In most cases, this would be the first instance in the first index of the first entry in a table. That's what we see here with the .1.1.1 instance of the table being returned. However, it is possible that the table may have no instances, in which case the agent would continue moving through the tree until a valid instance was found, potentially in a completely unrelated table. The set request allows a manager to change the value of an object on the agent. In this case, the manager must know the exact OID of the object to be set. Also, not every object can be set, as some are read-only. Additionally, it is possible to configure an SNMP agent or subagent to not allow objects to be set. When an object is set, the response by the agent simply echoes the new value. Now we get into our more complex interactions. The first is the walk request. A walk is really only visible to an end user, as the manager will translate the command into a series of getNext requests. The intent of a walk is to return all of the data within a MIB table or subtree. The algorithm used by the manager is perform a getNext on an object, usually the OID of the table. The agent returns the first instance of the first index of the first entry. The manager assesses whether or not the return value is within the desired table. If it is, it will do a getNext on the return value, which should then get the next item in the table. If it is not, the manager excludes the last piece of data returned and displays all of the previous data to the user. Let's take a look at an example of this. Note that the MIB objects in the agent that have an asterisk next to them are valid instances. The user executes a walk on 1.3.6.1.2.1.1.9, essentially asking the manager to fetch all of the data in the sys.or table. The manager translates this into a getNext on 1.3.6.1.2.1.1.9. The agent locates this in the MIB and immediately begins moving down through the MIB looking for a valid instance. It encounters its first valid instance at 1.3.6.1.2.1.1.9.1.1.1. This value is returned to the manager who, finding that the .9.1.1.1 is within the requested subtree, saves the data. The manager then repeats the getNext, but this time on the 9.1.1.1 object. Again, the agent steps through the MIB until it reaches 9.1.2.1. This value is returned to the manager, and the process is again repeated with 9.1.3.1 and 9.1.4.1. When the manager makes the getNext request for 9.1.4.1, the next instance found by the agent is 1.3.6.1.2.1.2.1. This value is returned to the manager, but the manager detects that the OID outside of the 1.3 is outside of the 1.3.6.1.2.1.1.9 table. It ends the walk and reports to the user all of the values from 9.1.1.1 to 9.1.4.1. Next is the get bulk request, which is only valid in an SNMP v2 environment or better. We will discuss the differences between SNMP v1, SNMP v2, and SNMP v3 in a later presentation. The get bulk, which is the easiest to understand of the complex requests, is similar to the get or getNext, as it entails a single request and a single response. The only difference, however, is that the manager can specify multiple objects on a single request. Thus, a get bulk could be recreated using a series of get or getNext requests, but is more efficient as it requires only a single request and response interaction. The bulk walk request is also valid for SNMP v2 only. You can think of the bulk walk as a mashup of a walk and a get bulk. The general algorithm is the same as a walk, but instead of being a series of getNext requests, the manager sends a series of get bulk requests. The result is that multiple tables can be walked in parallel. I would provide an animation of this, but the result would most likely be a steaming pile of spaghetti. Aside from requests, SNMP agents and subagents can generate traps. A trap is an unsolicited notification sent from the agent to the manager and is used to inform the manager of events occurring either in the SNMP environment or in the application space of one of the subagents. An example of this is a cold start trap, which the agent sends out upon initializing. This serves to notify managers that the agent is available for queries. Similarly, if a link goes down in the TCP/IP stack, the TCP/IP subagent may generate a link down trap. When a subagent generates a trap, it sends the trap to the agent, who then forwards it to the manager. The agent can also be configured to send a single trap to multiple managers. An inform is essentially the same thing as a trap. However, an inform requires that the manager acknowledge the receipt of the notification. This is only supported in SNMP v3 environments. Now that we understand the different components and interactions of the SNMP environment, let's put it all together with some animations showing some typical evolutions within SNMP. This first animation represents the startup of an agent on an LPAR where a single manager and a single TCP/IP subagent is running. What we see here is the stack representation, the TCP/IP subagent, and then below that the Unix system services space. The SNMP agent starts up and reads its configuration files. It then establishes a listen on UDP port 161 as well as opens an AF Unix socket with a path name temp DPI socket. The TCP/IP subagent, who regularly polls to see if an agent is active, sends a GET request to UDP port 161. The purpose of this request is to obtain the path name of the AF Unix socket the SNMP agent is using for its DPI communication. DPI, or Distributed Protocol Interface, is the language a subagent uses to communicate with an SNMP agent. It is over this socket that the TCP/IP subagent will connect to the agent for the duration of the subagent or agent's life. The SNMP agent authenticates the request and passes back the path name of the AF Unix socket. The TCP/IP subagent then sends a DPI open request over the AF Unix socket to establish a DPI connection with the agent. The TCP/IP subagent now issues a series of requests to the SNMP agent in order to register the different MIBs it supports. This lets the agent know what types of requests it can pass on to the subagent. At this point, the agent is initialized and the subagent is connected. The SNMP environment is ready to receive requests and/or send out traps. An SNMP manager may now query SNMP for information. To begin, it sends a request to UDP port 161. In this case, it sends a GET_NEXT request for if table. SNMP authenticates the request. Knowing that the interface MIB was registered by the TCP/IP subagent, the SNMP agent sends a DPI next to the subagent over the DPI socket. The TCP/IP subagent interacts with the TCP/IP stack to obtain the necessary information and then returns the first valid value in if table. In this case, ifIndex.1 with the DPI response. The agent then packages this into a response packet and passes the value back to the SNMP manager. That's all for this presentation. In subsequent presentations, we'll cover security models, configuration, and diagnostic approaches.